Thank you. Thank you very much. So yes, so I'm Julien. I am a research engineer at IJCLab in Orsay. And my current interest lies in exploring the transient sky using the Rubin alert stream. So first, what's the transient sky? So to state the obvious, we all know that the sky is not static. So it changes all the time. And by transient sky, we mean everything that changes in time or in space that moves. But of course, that's an umbrella to just which means many different phenomena over different over wide timescales. So there are things happening in our own solar system, so asteroids or comets or planets, for example. There will be things within our own galaxy, so variable stars, exoplanet transits, or even microlensing events when you have a foreground and background star, for example. And there will be things outside our galaxy, binary or merging stars or black holes. There will be supernova also within our galaxy, that's rare. There will be AGNs, gamma ray burst, as described by Regis just before. So there are many, many different things, and transient sky is not a unique thing. It's all those different phenomena happening at different timescales. I would love to explore transient sky. Currently, my main objective is to use the LSST. So LSST, sorry, I already made the mistake. So LSST changed its name recently. It's called the Rubin Observatory Legacy Survey of Space and Time. Fortunately, they keep the acronym, so you can keep using LSST, although it's Rubin Observatory behind. So what's the Rubin Observatory? So it's a huge observatory in construction. It will be deployed, it's being deployed in Chile, and it will start observing the sky in 2022. So we are not yet observing. And what's the idea behind LSST is usually when you want to make an observation with your telescope or observatory, you have to make a compromise. So either you look at the full sky, you want to like the full sky map, but you will be very shallow because you won't spend much time on each portion of the sky. So you won't be very deep. Or in the contrary, you will say, well, I want to be very deep. I want to go very deep in the redshift, for example, but I won't spend, I will spend a lot of time, so I won't get a full sky map. LSST is a bit like doing both, getting very fast. So every 3 days, or 3 nights actually, LSST will deliver a full sky map and very deep, thanks to its huge camera. So there will be a camera of 3 gigapixels. So it's exactly like your smartphone, but the size of a car, basically. So it's a huge thing. So LSST will be something like an observatory that will make a survey in a fast way and very deep. So of course, it will deliver, there is a price to pay, and it will deliver a huge amount of data. So each night that will be terabytes of data flowing, and there will be millions of alerts connected to transient phenomena. There is one problem, is most of the Rubin data products will be proprietary. So the raw data, the images, for example, that will be proprietary. So only if you have data rights, for example, you can play with the data. All the catalogs, they will be proprietary, so you will have to wait a period of 1 or 2 years before getting access to that. But one thing, the alerts that will be sent each night, those alerts will be public. That will be public data. How those alerts will be made, so each time you have a new observation of a field on the sky, there will be a reference image associated to that field. So what we will do is we'll make a quick calibration of this new observation. We'll make a difference between the observation and the reference, and everything that is left after the subtraction above 5 sigma will be considered as an alert, meaning that there is something new that wasn't before in the template, in the reference image. And by doing that, we plan to send about 10 million of those alerts each night. That's a huge number, and I will come to that later on. But those alerts will be the only public things for which you don't need to have the data rights. So if you take those 10 million alerts per night, great, and you say, well, each alert will contain, I don't know, photometry, some small cutouts. Each alert will be 100 kilobytes roughly. That's a stream of 1 terabyte each night that has to be sent from Chile to the US first, where there is the data processing facility, and then to France, where we have a site to process the data. And so that's 1 terabyte per night. And if you do that for 10 years, which is the length of the survey for LSST, you will end up with 3 petabytes, only just alerts. That's huge. So it's public, but it's definitely huge and quite difficult to manipulate on your own. So here on the below, there is a small cartoon. So what LSST decided to do is to say, well, we cannot simply send this alert to anyone. So it's public, but we don't have the pipe, the internet, the network pipe, to send that to anyone requesting the stream. So we'll make a selection, and we'll select systems that are called brokers. So those brokers, basically, they will receive the full stream, they will analyze the stream, and then they will be responsible of redistributing this stream, this process stream, to the community. So things are public, but there is a man in the middle called broker that will take the stream, process it, and redistribute that to the community. So of course, there are many problematics related to that. So the data is open, but if you think about it, the size and the heterogeneity of the data set make the things quite difficult. So as a broker, as a man in the middle, you need to be able to give access to the data at scale. Because when people will be sending queries or requests to your data, that will be a data exploration with multi-terabytes data sets, so even petabytes at the end of the 10 years. You should give them also the tools to do a reproducible analysis, so by versioning all the tools and the data that is coming. So when you have a survey whose length is 10 years, well, it's better if you version things. It's not a one-shot thing. And this has to be a sustainable effort. So the survey is for 10 years. So it's not just like you're taking data for 1 season and done. You will do that for 10 years, and the community will be asking you data for 10 years. So when LSST say, well, we'll open the data, the alert stream, well, we were all happy, but it was not enough. It should come with dedicated services. So actually, the load shifted from LSST to those brokers, and brokers not only have the data in hands, but they have also to develop all those services for the community such that the community can access this open data and do some open science. So early 2019, we decided in France to create a project such as a broker called Fink to tackle Rubin alert stream challenges. So we say, well, actually, we are very interested in doing that. We'll make sure that we can provide those services to the community in addition to this publicly available data. So Fink is a project with strong big data and machine learning components that's inherent to the size of the data set. It's a cloud-based analysis. So, well, I will come back briefly later on that. But well, with that scale of data, you cannot do that on your laptop or even with some supercomputer. Well, you could do, but it's streaming analysis, so it's quite difficult. So we decided to shift a bit our habits and try to work on the cloud. Fink is an international collaboration with, obviously, its roots in France, and you can see on the right the contributing laboratory in France, mostly in IN2P3, but not only. And we published our first paper this year, actually, so you can find the reference if you're interested, which include well, many co-authors from many different affiliations. And the project is led by 3 different people, so myself, but also 2 different researchers at Clermont-Ferrand, Emilien and Annelies. So what are our scientific objectives? So the goal of Fink is to collect and extract the science from the Rubin alerts and to give data access to the community. So it's a community-driven effort in a sense that we provide the structure, the infrastructure, we provide the services, but then that's the community that drives the science topics. They provide with us what they want to do. It's completely open source, so you can find anything online. And we have a prototype deployed at the virtual data cloud. So we are lucky to have here a cloud at Université-Paris Saclay called Virtual Data. so we could prototype the thing. At the beginning of the survey, at the beginning of the project, our current field of expertise include supernova and kilonova, so people who are hunting this kind of objects, extragalactic objects mostly. Microlensing, gravitational macrolensing events. We have also a strong component on the multi-messenger astronomy, so that include many things like gamma ray burst, binary X, neutrino astronomy, gravitational waves, many different things. So of course, what we are looking for is counterpart, electromagnetic counterpart to those signals. And we have also expertise in anomaly detection. So when you have 10 million alerts coming each night, of course, you can start to classify the things with known classes, like the supernova or microlensing. But obviously, there will be many new things that for which you don't have either a class or even a clue. And for that, you need to be prepared to not throw away the things, but try to understand whether those anomalous things for which you don't have a clue could be a sign of a new physics or a new phenomena, for example, that you would like to understand better. So we are preparing ourselves to that. And of course, because we are using, well, cloud-based analysis, big data things, machine learning, I wouldn't say it's new because, well, it's used in the community for a few years, but still it requires some teaching. So we are running periodically workshops and hackathon in order first to train people within the collaboration, but also to improve the global knowledge within the collaboration with all this fast-changing environment that is technology nowadays. So of course, LSST, or Rubin, is not yet online, so we are working on simulation, but also on real data. We signed an agreement with the ZTF telescopes. So the ZTF is a Zwicky transient facility located in California, in the US. So it's, well, you can see it as a pathfinder for Rubin. So it's like the Rubin Observatory, but in smaller. So we signed an agreement to analyze their data stream, their alert stream. So it's not yet at the LSST scale, but still it's sending a lot of data. So we receive from them, well, on the mean, 200,000 alerts each night. So you can see on the right detail per month. So per month, well, the y-axis is in million alerts. So per month is between, well, let's say 2 and 7 million alerts that we receive and process. Well, to realize a bit those numbers, well, gravitational waves, it's a few alerts per week at maximum, and we are at 200,000 alerts per night. So it's a completely different regime that we have to explore. So thanks to this stream, we can start to do some science first and prepare our infrastructure for LSST. So since the beginning, I'm talking about alerts, data stream, that will be public, etc. But I didn't mention what's inside an alert, what exactly is an alert and what kind of information is made public. So as I said at the beginning, alerts are based on difference image analysis. So you have your new observation, you have a reference, and you make a difference between the two. And the alert is what's left after the subtraction. And so each ZTF alert, and that will be the same for Rubin, it contains a number of different things. First, information about the new detection. So an estimate of the magnitude, an estimate of the error also on the magnitude, its position on the sky, some calibration information, etc., etc. So just information about this new detection. It contains also information about the neighbors, whether well, close to that alert, there is something already known from existing catalogs. And for that, we are cross-matching each alert with Gaia, for example, the Gaia catalogs or Pan-stars. We are also using a lot the tools from the CDS at Strasbourg that provides a number of catalogs. The alert also contains historical information if the object has been seen previously. So obviously, if you have like a variable star or if you have a supernova, which already exploded, this object will periodically emit new alert each time you will look at it. Well, instead of you as a user getting back to the database, trying to connect this new observation to previous one, this history is already included inside the alert, so that makes the analysis quite easier. And last, there are also small images that are provided, small images around the detection. So you can see that at the bottom. So at the top, it's a light curve. So you have the magnitude, for example, as a function of time. And at the bottom, you have the images, so cutouts. So these are 60 by 60 pixel images, so quite small. And you can see here is an image of a supernova within a galaxy, type 1a, supernova type 1a. So you have the galaxy. So on the left is the new observation. So you have the galaxy, and in the middle, what generated the alert, which we think it's a supernova type 1a. In the middle, you have the template, so the reference image. The color scale is not the same, so that's why they look a bit different. And on the right, you have the difference images after calibration, after we calibrate the two. And you can see what's left is mainly this bright dot at the middle, which is the supernova. So what we do in Fink, so we collect those alerts. So over the last year, for example, we collected more than 60 million alerts, and we processed 18 million. What's not the same because we flag many bogus or artifacts, for example. So there are many things that are not real alerts, so we have to discard them. And once we have alerts, we have then a series of modules that try to extract the science from each alert. And we have two kinds of things. We have cross-match. So we take the alert position and we make a positional cross-match with existing catalogs. So whether there is something known already in the literature. And we do that a lot with the Strasbourg tools, the CDS tools, the cross-match service, for example. And we have also modules that try to classify the alerts. So they are usually based on machine learning, but not only. We have, a number of different classes, including supernova, microlensing, solar system objects. And we are trying to put those alerts inside boxes, inside those classes, and see whether we can tag them and put a label. And on the right, what you can see is the projection of the ZTF stream based on our classification for different classes. So for example, the top left is all the solar system object candidates. Well, we are lucky, they are mainly along the ecliptic plane, so that's good. That's where you are likely to find asteroids and solar system objects. You have also microlensing candidates, mainly located around the bulge of our galaxy where the density of stars is higher as seen from the Earth. And then you have supernova candidates, for example, or variable stars. So we're trying to do many different things. And then once we have that, we redistribute that to our users directly. So how our users are accessing the data processed by Fink. So there are two entry points for users. The first one is getting the live streams. So at the end of the processing, the users, they can define a filter. And a filter is something that say, give me, for example, all the supernova candidates, or give me all the solar system candidates. And they will receive directly all the candidates that satisfy this criterion. So of course, that's a huge reduction of the initial stream, which was 1 terabyte per night. And usually we target something with 100, I don't know, maximum few hundred per night. The data is received live. So I don't have a demo, but I wanted to show you, for example, that's the data for the night, for this night. So, well, the 15th December 2020. So we received this night roughly 270,000 alerts. So you can see it started at 4 a.m. in the morning, and it stopped at the very beginning of this workshop. And here is the detail for each night. Sometimes each night you have almost 1 million. People can then subscribe to substream. So here is another thing. So here we have different streams, for example, for early supernova candidates. So you can see that, I don't know, at 1 p.m. this afternoon, there were 2 early supernova. So then they will receive that and they will assess whether or not these are good candidates for follow-up. And I will come back later on that. And the second thing that we propose to our users, the second service, is a science portal. So Science Portal is just a web application where people can explore the full Fink data set in their browser. There is a REST API also where they can query the database and receive the data back. All data will remain accessible for the full survey duration. Keep in mind, this is 3 petabytes that is expected. So it's open data, but still you need to have a huge infrastructure to serve the community. And currently, the science portal is online, and there are several terabytes of data that is already accessible to the public. And it's deployed on the virtual data cloud. And I have a small demo. So here it is. So you can click. So you can either explore the data or cross-match your own catalog with all the Fink data. So for the moment, that's ZTF, but that will be LSST later on. So if you're interested in cross-matching, for example, your experiment data with LSST, you can do it online directly or via the API. So here you have the interface. You can query the things. So for example, I don't know, give me all the early supernova candidate of this night. It will give you a list. So there are terabytes behind the scene. You can click. And it will open all the data that we have about this object. So for example, here it's Noise Galaxy, where supernova exploded, well, 2 weeks ago, actually. And we have the data. And then you can focus a bit more on, for example, look at the object, whether the machine learning scores, they are telling you something more, etc. There are many things you can tune. So that's completely user-driven. So you have different tabs proposed by the community about variable stars, microlensing, solar system objects, gamma ray burst. And so it's really like community-driven effort. Sorry. Okay. I don't know what. Last thing I wanted to talk is coordination and interoperability. So Regis mentioned it before, and I think it's quite important actually. So I was talking about the alerts sent by the Rubin Observatory. There will be plenty, millions. But despite the number, we know that it's not the only part of the story. And we need coordination with other facilities and follow-up resources to extract all the science that we would like to do. First of all, because LSST is bounded in the spectrum. So it's only doing visible or near infrared, but we don't have information beyond that. So we need information from the other part of the electromagnetic spectrum, but also from different messengers, so gravitational waves or neutrino. And of course, more diverse data means better science analysis. But there is always, the difficulty is not to gather the data. Well, it's a wishful thinking, or it's easy to say. The difficulty is to really build tools to interoperate between different collaboration or different users. Because we are all in our daily life or daily collaboration life, designing our own tools, sometimes, and me first, reinventing the wheel, while there are standards existing out there. They are probably not perfect, but if everyone is willing to work on the standards rather than reinventing a new tool, that will be probably easier to talk to each other. So we have to coordinate not only within our collaboration, but with existing follow-up resources and different surveys. And here is an example, for example, in Fink, usually at the end of the night or during the night, during the processing, we propose our candidates to other telescopes or collaboration for follow-up. And for that, we have to use a common language. Not only just, hey, we have something interesting, but actually something from the computer point of view that makes sense, that they can interpret straight away and launch follow-up observation if needed. And so in Fink, we propose things, we translate that into this common language, they observe, they confirm or not, and then they translate again into this common language so that in Fink, we can update our database later on if there are new things. And by doing that, for example, in Fink, we had many follow-up for supernova type 1a, supernova type 2, etc., etc. So take-away message. So Fink, this project that I just presented to you, is a broker designed to tackle the Rubin alert big data challenges. So we are trying to enable science by applying this state-of-the-art technology because of those huge data volume. The data is publicly available. You can already take it, do whatever you want. And we also host new projects. So I told you about supernova and microlensing, but definitely there are many, many different things to do with Rubin. So feel free to join. Rubin is doing the selection of the different broker team that will be officially processing the thing. So Fink is one of them, and finger crossed will be selected. And of course, I highlighted the difficulty in exploiting this open data. So we need to develop the different services, not just opening the data. That's not enough. We need to provide training and teaching about new techniques as well, because people, well, sometimes tools are difficult to use to exploit the data. And I think it's, Agatha also mentioned that or Eric, is that it's not only you need to give the data, but you need to give the recipe to exploit the data. And I will conclude by saying it's very important, I think, to enforce an interoperability and by developing standards and common languages. And I would cite the IVOA, this International Virtual Observatory. But they are not the only one, definitely, but I think they are very good thing to follow. Thank you very much. I'm done.
Thank you very much, Julien. Thank you. It was very interesting to see how crucial it will be, the fact that we will have to sort the information with this very huge amount of data. It's really impressive.
Thank you.
So we have a small, short 5 minutes for questions.
Yes, so we have a question from Norma Graciela Sanchez. So please ask your question.
Thank you. Thank you very much for this interesting presentation. I have 2 points mainly, which I don't see. I mean, given the interest of LSST Vera Rubin instrument, is Fink the only way to have all the alert of big data challenges, or there are others which you coordinate because it's a huge, it's a huge amount of different scientific problems to tackle. And the second point, and related with this, is that you mentioned the transient sky with different, of course, with all different multi-messenger and so on. In order to catch, really new or discoveries, say, how do you implement with the scientific programs here? How do you target? You have a way to catch the data, to collect the data, the alerts, but also I assume there are already preparation and scientific programs which in some sense too are targeting to, for instance, in dark energy, in dark matter, which are related also with the work you are, looking for.
Mm-hmm.
So how do you prepare? Because once you collect, and I think, it's a powerful way to all these big data challenges collect, you also need to analyze and interpret, and to extract the better benefits. Thank you.
Thank you. So 2 questions. So concerning the first one, we are not the only one, exactly. So there are 15 ongoing projects currently competing to get to be a broker in LSST or in Rubin, and LSST will select 5 to 7 of them. So it's a ratio 1/3, 1/2, roughly. So the competition is ongoing. We know who they are. We are collaborating with some of them, trying to gather gather the different communities. And as you rightfully say, one broker cannot do everything anyway, because there are so many science topics, and our team is limited. So eventually what LSST will do is to select the broker in such a way that all the science topic will be covered, not by only one, but by all of them, let's say. So if you're interested, I could follow information about the others, what they do. There are brokers that, like Fink, are trying to cover different science topics. And there are brokers, however, that are focusing on very single science topic. Like, for example, there are brokers saying, no, me, I'm only interested in solar system objects, for example. And they will reject everything else. So there are those two kind of categories.
Thank you. It could be very interesting to know, for instance, at the level of France, or I mean, how, which are the different network in some sense in which you are, or at the level international too, to tackle, I mean, to target with the scientific of the teams, to target and to extract the better benefits from the different data. That will be an useful information.
That's correct.
About
so in France, so we are in contact with different networks in France and at the international level. And that, I think that solves that gives an answer to your second question. So how do we connect with others? So usually to make target of observation, target of opportunity, for example, or things like that, to make sure that our observation will be used by others. Yeah. For that, we directly talk to people. And I have very concrete examples. So we are working together with the SVOM collaboration. So SVOM is a satellite and ground-based experiment that will be launched in a few years, same time scale as LSST actually. And so we are talking already with them how to connect efficiently Fink with their alert system, such that one way or the other, either they have something or we have something, we can react and we can share information. That's the first thing. Second thing is GRANDMA. GRANDMA is a network of telescopes, and I think Sarah will talk about that either later today or tomorrow. And we are working with them already, such that we can feed GRANDMA with Fink alerts, such that they can optimize their observational strategy given what Fink is providing. And vice versa, if GRANDMA has something, it will alert Fink such that we can look in our data whether we find some counterparts. So that's the way we work. We are talking with people. That's a bit pedestrian because you have to talk, but that's working.
Okay, we have a second question by Eric.
Yes, hi Julien. It's nice to see Fink progressing. I'm a big supporter of the project.
Thank you.
I've seen earlier in your demo, it was nice to see Fink working on actual images there, but I saw a tab with GRB. Is this functionality is working already? And can you showcase a bit with GRBs?
Damn it, you pawned me. No, it's not working yet. Well, it's working behind the scene, but it's not publicly available. So that's the work with SVOM, with the people from SVOM. So actually, for the moment, we are experimenting with Fermi and Swift data. So what we do is we collect the data from Fermi and Swift, and we cross-match them in real time with the ZTF stream, and we try to provide counterpart. And the reason why I don't showcase it now is because we don't have any counterpart to show. No zero signal for the moment. Well, shall I tell the truth? So ZTF is a bit bizarre. So ZTF is a private public funded survey. So part of this data is private, part is public. And we signed an agreement with them on the public side because it was easier to start with. And of course, all the interesting things on the GRB side is on the private side. Right. So we don't have access to it. Fortunately, with LSST, if we are selected as an official broker, we won't have this problem and we'll have the full stream without any restriction. Okay. So wait a bit and this tab will be functional.
Very good.